So thanks to the organizers for giving me the opportunity to talk about our work in this conference. So as the title says, I'm going to talk about our recent experiments on how we can engineer the electron-phonon coupling in metals by using or by constructing interfaces of two different metals in heterostructure. This heterostructure is itself not a layered two-dimensional material, as many people have talked about here, but we'll see that the fundamental electronic processes are crucially dependent on the interactions at this two-dimensional interface of the different metals. So this work was done, this was started with a collaboration with Professor Arun at SSU in IISc, and then we carried out the experiments in Professor Arindam Ghosh's lab, along with my colleagues Tuhin, Bonasri, Binita, and Sai. So this will be there. Oh, it's okay, it's visible, it's fine. So the electron-phonon interaction in a system is actually very crucial because it impacts multiple fields, starting from making new superconductors to making new thermoelectric, polar, and optical materials. So the effort to modulate the electron-phonon interaction in any material has been underway for a long time, and how one modulates this varies from one system to another. In metals particularly, I have listed some of the methods which are not completely exclusive to each other. So one can create quantum wells where the states in a quantum well are perfectly aligned with the Fermi level that can change the electron-phonon coupling. One can reduce or can make low frequency phonons by making surfaces, for example, in tin nanowires. The scattering from nanoparticle interfaces can increase the electron-phonon coupling. Then in an example where SR-TiO3 is grown on FESC, one can show that the TiO bonds at FESC can couple to the electrons in SR-TiO3 in certain annealing conditions, and that can also enhance the electron-phonon coupling. Then there are methods to optically drive the lattice. For example, in bilayer graphene with terahertz spectroscopy, there have been some proposals and work to show that you can excite the particular bonds, whatever you want, and then that can also change the electron-phonon coupling. And then stress is another way where you can modulate your lattice by application of stress, that like compressive stress will reduce the bonds and tensile stress will enhance, and that will also change the coupling. But all these efforts have given an enhancement of electron-phonon coupling, has shown an enhancement by about a factor of 2, which is quite a high enhancement, but it has been difficult to cross this kind of factor in any material so far. So that's what our aim is. We want to show a platform for changing the electron-phonon coupling by creating a dense network of crystalline interfaces. So as I showed some examples in the previous slide, and as also many speakers have talked about, that interfaces can crucially impact your electronic scattering in a material, and that's what we try to utilize over here. Our approach is to embed metal nanoparticles inside another metallic matrix and place these nanoparticles very close to each other, where the interfaces are very close to each other. And I'll show that how the interactions will change the properties of the system. However, the challenge is that this particular structure that I'm proposing over here is built of metal nanoparticles put inside another metallic matrix. And it has been, in general, a difficulty to assemble metal nanoparticles into a metallic matrix. And that is because a nanoparticle, when it is formed, is capped by surface agents for its protection. And removal of these agents typically destroys its structural integrity. So when one tries to make an assembly of nanoparticles, the ligands or the surface capping agents form tunneling gaps. So in the transport measurements, one usually gets an insulating transport. So this is a picture of gold nanoparticles and of a scale about 10 nanometer, and the transport is shown in this graph. So that the conductance goes to 0 at 0 temperature, which means sample becomes insulating. So the first challenge is to first design a material built of metal nanoparticles by removing these ligands or capping agents. And so the particular approach that we have taken is a core shell nanoparticle. We first build these core shell nanoparticles, and we have chosen gold and silver particularly because of the identical lattice constants, which will allow us to make a crystalline matrix. And then by removal of the ligands, we'll fuse this core shell nanoparticles into a cookie structure. So the silver nanoparticles will be embedded inside the gold host matrix over here. And we want to tune the structural parameters of the radii of the embedded silver nanoparticles and the separation between the silver nanoparticles. So I will just quickly go through on how we do it. The details can be found in this paper. So we first take a silver salt, then we chemically reduce this salt to a silver nanoparticle, and then in this we add another gold salt, and the structure formed is a silver core and gold shell nanohybrid. These are then fused at different stages to form a metallic network. So you can see I don't know it's visible from the backside, but this is a cookie kind of picture where you can see darker patches inside the bigger circle. So those are the embedded silver nanoparticles, and this one is a aggregated structure for that. Then by using certain chemical treatments and thermal treatments, we remove all the surface capping agents and then assemble this into substrate. So the shaded region over here, this pointer is not working, but okay, so the rectangular region over here indicates the substrate, and these are the nanoparticles that we deposit on the substrate. Then after chemical treatment, we form a film like that. So the black circle in this graph over here indicates our film, and these are the triangles are chrome gold electrodes which we use for transport measurements. So that's the basic protocol that we have been using, and this has allowed us to gain tunability over two structural parameters. One is the silver nanoparticle radius, which we call RAG, and another is the filling fraction, the relative fraction of gold to silver. So F equals to 0 means pure gold film, and F equals to 1 means a pure silver film. So we can vary this F from 0 to 1 as we want, and that into the control we have in our experiments. So first, for F equals to 0, which means a pure gold film, what we see is a metallic transform. This is a plot of the resistivity as a function of temperature, and the different traces indicate the different sides of a sample, which means that the sample is homogeneously metallic, a pure gold film as expected. And now when we put some amount of silver, which means a finite non-zero F, we see that we do have a metallic transport. All the channels are reducing resistivity with decreasing temperature. But we see that the transport is not as metallic as gold, and we start seeing a saturation of the resistivity at higher temperatures. So we have solved the first challenge of making a matrix like this, and we also start seeing signature of the non-triviality of the transport due to the embedding of silver inside the gold. So looking at the numbers of the resistivity, what we see is that if we keep the silver nanoparticle radii fixed, as we can see from the red points, and vary the fraction, the resistivity, rho naught is the residual resistivity or the resistivity at base temperature. This indicates the impurity resistivity. The resistivity increases with the filling fraction. So the more you have silver, the more is the resistivity. And alternately, if we keep the volume fraction of silver fixed and change the radii of the silver nanoparticles, what we see is that the resistivity decreases as the radii is increased. So overall, this means that the interface, the residual resistivity or the resistivity of the film changes with the overall interface area. Now this seems to be quite intuitive, because after all the gold-silver boundaries are nothing but disorder or imperfections in our crystal. So this will of course form a source of scattering, which will increase the resistivity. What is surprising here is that the amount it has increased to. So a pristine gold and silver has a resistivity of about 0.1 micrometer. What we show here is a resistivity of about 30 or 20 micrometer, which is 200, like 2 orders of magnitude higher than the pristine gold or silver. And typically it has been shown that with grain boundaries or imperfections, resistivity will at most increase by a factor of 5. Whereas this kind of enhancement is unexpected, and specifically when it reaches this limit. So what is a Morto-Afferagel limit? We know that in a metal, the scattering length changes with temperature. The scattering length decreases with increasing temperature. However, it can only decrease till the extent of the interatomic spacing, because after that your quasi-particles will not be well defined. So this is an empirical formula, and we can get some numbers for a particular system. What we see is that for pure gold and pure silver, our resistivities are okay, but when in an intermediate regime, we hit this number, which means that we are making something called bad metals, which show this kind of resistivity. And to give an example of bad metals, this plot over here shows that, for example, copper, many materials melt well before this kind of temperatures are reached where the resistivity is so high. And some other metals or elemental superconductors, especially high TC cuprates, show saturation before, like when it approaches this kind of resistivity. So what we see is that gold and silver, which are apparently two like very simple noble metals, start showing this bad metallic behavior, and it is accompanied by the saturation and resistivity. So to show that, this plot shows the temperature dependent part of the resistivity. The residual resistivity has been subtracted, and the rest of the resistivity has been plotted with temperature. what we see is that the saturation is increasing with increasing silver, and this is not captured by a conventional electron-phonon form. The dotted line over here shows that, so in a good metal, the dominant source of scattering are the electron-phonon interactions, and we see that if we try to fit the data with that, it of course does not fit. There is a saturation or a deviation at higher temperature, and this we have tried to capture phenomenologically by a parallel channel transport. So this is not like a conventional parallel channel that is being used to capture or explain bad metals in general. So here we say that we have two components or two parallel resistors which are parallel only to the temperature dependent part of resistivity. So you can see that the denominator in the left hand side has a rho t minus rho 0. So only the temperature dependent part, and this parallel, okay, and this parallel channel is a constant. We have kept it a constant at the Morta-Afferagel limit, and we see that this actually captures the data. So the origin of this channel and why it behaves like this is unknown to us, but it captures the data, and not only that, we can extract two fitting parameters from here. One is the Debye temperature, which is about 160 Kelvin, that is close to gold, and another is the electron-phonon coupling parameter. So just to give you an idea, the electron-phonon coupling strength for pure gold and silver is about 0.1. So what we show here is an enhancement of about 100 times in the electron-phonon coupling strength. Now, since this has been extracted from a fitting, which is itself phenomenological, to extract the phonon coupling strengths, we have done a separate set of experiments called the point contact spectroscopy. Earlier today, it was mentioned in one of the talks. So this is similar to an STM-based technique where you bring a sharp tip closer to the system. But unlike STM, here the tip actually touches the sample through a resistance, which we call the point contact resistance. And the idea here is that suppose you have a ballistic contact or an ideal contact where there is no scattering at the orifice, you can inject electrons with arbitrarily high kinetic energies into the sample, which is otherwise not possible in a diffusive transport. So now say if you apply a bias between the tip and the sample of EV magnitude, this extra additional energy will be dissipated into the sample by dissipation with available scattering modes, which in the case of metals are phonons. So what we get is that if you have the point contact resistance and if you do a derivative of it, you will see that it closely resembles the phonon density of states, which we call the Migdal-Eliashberg function that resembles the phonon density of states. And this will look something of this sort. When you have the highest number of phonons, the change in resistance will be high. When the number of phonons, when at sufficiently high energies, when the phonons are not there in the density of states, you do not have any change in the energy. So from here, one can extract the electron-phonon coupling parameter. In principle, and a contact is never ideal. You always have diffusion or some sort of scattering at the orifice, especially in our system when we suspect a lot of disorder. In this kind of situation, this spectrum is just modified with a background term. You have an additional non-zero constant value coming up at higher biases, and the reason is that now the phonons that are being generated will get trapped at the orifice. So you have a cumulative effect of all available phonons, and that is directly proportional to the electron-phonon coupling strength. So with these experiments, we have found out the electron-phonon coupling strength. This is an example for pure gold film where we see that, okay, we have the strength as expected, and the peaks come up at the Van Hoff singularities of the phonon density of states. So for gold and silver, it's close to 10 and 20 MeV. So now moving on, what we see in our system is that this is the point contact spectra, and we see a peak at about 18 MeV that resembles the acoustic phonons in gold. This shows that we are indeed picking up the effect of electron-phonon coupling in our system. And with changing silver fractions, we see that the background increases. This means that this is how the electron-phonon coupling looks like. For 0 and 1, which means pure gold and pure silver, we have a value less than 1. But in an intermediate regime, it goes to as high as 20 or so. And in a compilation of the electron-phonon coupling strength in different materials, this is what it looks like. So this graph over here shows, in the x-axis, it is the lambda, the electron-phonon coupling strength. And the y-axis shows the room temperature resistivity of different materials normalized by the MIR limit. So this shows that we have, the purple points show that we have the highest electron-phonon coupling strength shown in this material. And the next question is, from where does this come? So what we suspect is that the charge transfer at the interface of gold and silver could be a reason contributing to this. So whenever you form a heterostructure of two different materials, due to the difference in on-site potential, there can be a finite charge doping. And via XPS measurements, we have actually probed this charge transfer. And what we see is the lambda varies monotonically with the amount of charge transfer. That is the amount of charge created at the interface. To understand this, there have been some theoretical calculations by Shenjon and Manish and HRK that they have shown that in a square lattice, if you just take a toy model of square lattice, they have shown this is a charge distribution. By keeping up on-site potential difference, you can have a finite charge. And in their calculations, they show that this is how the lambda can go up in principle. The reason is that due to the interfacial charge transfer, now your electrons can couple to these interfaces through electrostatic interactions, the Coulomb interactions, and the interfaces can host their own set of phonon modes called the localized phonons. So this can indeed lead to the enhancement in lambda, which is a possibility. However, the open question is why will this depend on the fraction of silver? So with this, I'll conclude. So we have shown the bottom-up approach to make a metal nanocomposite. We show an unconventional metallic transport in gold and silver, resembling bad metals, and we show that these buried interfaces can lead to a very high electron-phonon coupling in these intrinsically weak metals, weak coupling metals. This leads to another set of questions altogether. What is the origin of this high electron-phonon coupling? Though we say that, okay, the interfaces can be a reason, we have no answer as to why the charge transfer will depend on the interfaces. And of course, the questions are why isn't it still an insulator, polaronic or Anderson? So we suspect that there could exist coexistence of localized and attenuated electrons in the system. So you can find more details in Arindam's talk on 26 July. And thank you for your attention.
Questions?
Yeah.
We have different electron-phonon coupling.
Yeah, so right. In the point contact experiments, what we get is that this is the acoustic phonon modes. The 18 MeV is the acoustic phonon modes. But there is a possibility that there are optical phonon modes, low frequency phonon modes, which are not showing up in the transport experiments. Because in the theoretical simulations, they say that, okay, it is possible that the surface phonon modes, which are optical phonons, can couple strongly. So that is not there in the transport experiments. For that, one probably needs to do some neutron scattering to see the phonon density of states. But by this, I just know the cumulative phonon coupling strength, which takes all the phonons into consideration.
Modeling, the enhancement was not that much though.
Right, so because if you see in our charge transfer, what we measure experimentally is about 0.6 electron per site. What they have shown is still 0.09 electron per site, the delta n in the x-axis. And that is because given, and so the work function difference between gold and silver is intrinsically 1 eV, which will give you a charge transfer of 0.01. What we see is in experiments is very high than that. So this part is not mimicked in the experiments, and for that they have kept delta n as a free parameter. And they have shown that enhancement is possible in some sense, and this is the normalized enhancement, lambda calculated by the 0 delta n lambda. So that part is still a puzzle, that why the charge transfer is there so much, and why is it dependent on the positioning of silver.
Any more questions? Nice talk. I'll ask you the same question I asked Arindam and I didn't get an answer, which is what are the implications for superconductivity?
Yeah, so in an ongoing set of experiments, actually we see, I think Arindam will talk about in his talk, that we see that there are two possible phases coming up in the system. We do see some phases insulating, and we do see some drops in some places, but these two are inhomogeneous in nature. That's why I mentioned that there can be a possible coexistence of localized and attenuated electrons. So even if there is a state like that, the fact that we have to get it globally is a challenge to us. At what temperature? So, I mean, we do see features coming at like 150 Kelvin, close to the Debye temperature itself. So that's.
Any more questions? Are there any questions online?
I think. This is a thick film. It's a 3 micron film made of this 20 nanometer balls of gold and silver. So you mean to say the thickness is reduced? We have made films of like of different dimensions and all, but I think what we believe and what we have got in our experiments that this is independent of the like overall dimension. It does just depends on this individual entity of the gold silver hybrid. Yeah.
You take it to be T power 5 as well, right? In your
Yeah,
earlier
it's
modeling.
3 micron in our experiments. Yeah, but we have gone like lesser by like 1 micron, not more than that, like less than that.
Okay, are there any questions from online participants? If so, please unmute and ask. Okay, if not, let's thank Shreya for a very nice talk, and